simplify even more. So now our U84s are just these solid, large blue or green spheres. And this is cubic closest packing arrangement again. And now in the tetrahedral holes, we've got isolated hexamers. And what the blue and the green represent is this is actually two interpenetrating networks of these U84s linked by hexamers in a tetrahedral arrangement. So the blue is one network and the green is the other network. And where's the erbium? The erbium, again, in a monomeric form, bridges these clusters together in the tetrahedral arrangement. Okay, so in a moment we'll summarize what's the periodic trend here. But first, let's take a look at what happens with transition metals as our counterions now. Okay, so now we're not working in sulfuric acid because transition metals dissolve just fine in water. And we're using divalent transition metals because we don't want to use such high oxidation state metals that might oxidize the uranium to hexavalent uranium, because the tetravalent form is indeed the less stable form in most conditions. So we've done this reaction with chromium, manganese, iron, cobalt, nickel, and zinc, all in the divalent form. So now what we get is this beautiful wheel cluster. So we still have this hexamer building unit going on, or theme. So the green are the hexamer units, and there's 10 of them in this wheel, and they alternate with monomer units, and there's 10 of those in blue. And so for a total of 70 uranium polyhedra in a wheel. But now we're working in water, not acid, so we've got less sulfate, and we can get more extensive hydrolysis reactions. And so our hexamers, rather than bridged by sulfates, they are fused together into this cluster structure shown here. All right, so what do the counterions do? In the case of manganese, they undergo this kind of staggered stacking. Here's two views of it, really beautiful structures. Now with zinc, we see something different. So zinc, whereas with manganese, the manganese reside between the clusters and link them together. With zinc, they tend to hover above and below and far less extensive linking. In fact, we see some zinc monomers that are just bonded octahedrally by water that don't link the clusters at all. So it turns out that we can dissolve these clusters in organic solvents. So THF with some butylamine added, or really any kind of long chain amine, and we get really beautiful scattering data. So this is some of the most beautiful sacs I've ever seen. And what we see is the manganese and the zinc follow similar trends in solution that they follow in the solid state. So the pink is the scattering curve for the manganese U70 cluster. And we can fit this as a cylindrical stack of 8 of these U70 rings, all stacked together in this eclipsed form. So we don't see this at all in our solid state structures as crystallized from water, but when we redissolve them with these amine caps, I'll call them, they tend to form different assemblies. And we think that they're actually forming inverse micelles, and that's what's promoting this stacking of the clusters. The scattering curve with zinc is the black, and we've got a shift in our Guinea elbow, so this means our species are by and large much smaller. And the green is the simulated scattering data for just an isolated ring. So that's what we predominantly have in this solution is isolated rings. And if we can combine like 10% of linked clusters and simulate that scattering data with 90% isolated rings, we get something that fits a little bit better. So, so the bottom line is the manganese that links the clusters together in the solid state, it links them together in solution, whereas the zinc doesn't link them together so extensively in solid state. It doesn't link them together in solution either. And this has to do with the ionicity. So zinc is, you get more ionic metal cations as you go across the transition metal series. Okay, so this is to summarize the first scientific story that I wanted to tell you. Basically, we can do In practice, at least on paper, simple chemistry, starting with uranium sulfate monomers, we can add transition metal or lanthanide counter ions, and we get this beautiful self-assembly of clusters and clusters of clusters and superatoms, and so on. So I already talked about the difference between sulfuric acid versus water, more extensive hydrolysis, more linking by sulfate. But what about this transition from a covalently linked framework of hexamers to the lanthanides just becoming decorating and linking of these U84 clusters? Well, as you go across the lanthanide series, again, you've got more covalency in the early part of the series and more ionicity in the later part of the series. So in the later part of the series, these lanthanides can truly act like traditional counterions, whereas in the early part of the series, they're more traditional framework formers. We also did magnetic measurements on these compounds, but no time to talk about that now. This is for you, Kyriakos. Okay, so switching gears. The next scientific story I'd like to tell you, so we're still sticking with the theme as clusters as building blocks for materials, but now we're looking at clusters that are used in nanolithography of microelectronics. So our society is demanding higher density memories, smaller memories, and you really need to get to the atomic level of patterning to get these kinds of features as shown on this computer chip here. So the chemistry that we're talking about here, and this is something that, this is really the chemistry that brought me to Oregon State University and I've collaborated with Greg on since I've been here. This is lithography of hafnium dioxide. Hafnium dioxide is both a hard mask in microelectronics as well as a functional material. It has a high K dielectric. And the chemistry is as follows. So we start with a precursor solution of hafnium oxychloride, more on that in a moment, and hydrogen peroxide and sulfuric acid. So pretty harsh solution. This is spin coated onto a substrate and dehydrated, and then this substrate is masked. And so think of putting a window screen down on top of the substrate, and what is exposed is irradiated with UV, and this causes some chemistry to happen, so some light-promoted chemistry. And what the chemistry is, to the best of our understanding, is disproportionation of the peroxide to form oxide linkages between the hafnium. So the hafnium, you form basically hafnium oxide that becomes insoluble. Okay, so then you take off your mask and you expose the entire substrate to what's called a development solution. And this dissolves away the unexposed portions, leaving behind the exposed portions as your patterned hafnium oxide. Okay, so the form of the hafnium that goes into this precursor solution, it is a cluster. In fact, it is 4 hafniums that are linked together into a flat square bridged by dihydroxides, about 1 nanometer in size. And we've studied the development solution. And so what comes up in the tetramethyl ammonium hydroxide solution is also a cluster. So we can actually see where our peroxide is. It bridges the hafniums together into this hexamer ring. Okay, so why are clusters important? So this is a picture that was taken by Greg's group in a publication in 2014. This is a TEM image of patterned hafnium oxide. And this feature shown here is about 10 nanometers in diameter. The clusters are 1 nanometer in diameter, so they're small and they're all the same size. And you can see the importance to get these straight lines and these very small features. You can think of how important it is to both deposit and pick up your clusters, or pick up your building units as discrete units that are all the same size. And so that's what the clusters gives us, small, very discrete units. Okay, so we had studied the development solution. We found that a cluster existed there, but now we wanted to study the deposition solution. We want to know exactly where does the peroxide go in relation to the hafnium oxychloride, that hafnium tetramer. How does it interact with it? So the first study that we did a PDF study. So this is PDF, paired distribution function from total X-ray scattering. It basically shows you interatomic distances within a solution. Okay, so we've got two PDFs here. The black is the freshly prepared solution, and the blue is 1 week age. So this contains only that hafnium tetramer plus the peroxide. And we normalize the intensity of these two spectra to this peak at 2.2 angstroms, because this is the distance of a hafnium oxygen bond. And regardless of what the speciation is going to be, you're always going to have 8 to 9 of these hafnium oxygen bonds. So then we can see how the relative intensity of the other peaks change. This second peak is bridging hafniums within this square, about 3.5 angstroms. And then these other two peaks, this represents the diagonal correlations. But notice in the freshly prepared solutions, we don't see those at all. They're missing. Okay, so our hypothesis is that the peroxide chews up these squares into dimer forms, and then after time, they reform. And so we can see those diagonal relationships. Okay, but we still don't know where the peroxide is. And so we are crystallographers at heart. We like to see things, evidence in the solid state. So we went to crystallize this hafnium peroxide form so we can really know where it is. So to do this, we need to eliminate the chloride because the chloride is redox active. So we replaced it with chlorate, perchlorate counter ions. So we dissolve hafnium carbonate in perchloric acid and then add peroxide. And we did successfully obtain the tetramer, and we can see that the peroxide does sit in the bridging positions within this tetramer. So our hypothesis and analysis of the solution data was indeed correct. We have not published this yet. We are currently working on it, and we haven't published it yet because we decided to do the same thing with zirconium and got distracted because the results were really quite surprising and unexpected. So when you add peroxide to aqueous zirconium square tetramer solutions, what you get instead is this oxo-centered tetrahedron. So the peroxide has completely chewed up this tetramer that is really the ubiquitous form of hafnium or zirconium in aqueous acid, and it's reformed it as a different arrangement of 4 hafnium centers. And there's our peroxide, again, in a bridging position between 2 hafnium centers. Okay, so this is a very aggressive reaction with 10 equivalents of peroxide per zirconium. Now, if we cut back on the peroxide and just have 1-to-1 peroxide to zirconium ratio, instead we isolate this beautiful zirconium 25 wheel. So there's 25 zirconium centers in this wheel structure, and again, our peroxide is located in these bridging positions. Okay, so we got these 2 structures. We were quite excited about it. We wanted to publish it in JACS, but we needed something more. So we tried catalysis. It failed miserably. So we decided instead to just go for the pure fundamental chemistry and try to understand how they form, because that is really what's interesting here. And knowing that hafnium does different chemistry, what's the difference? Because zirconium and hafnium are the most similar elements on the periodic table, yet we're seeing very different chemistry, chemical reactions with peroxide. All right, so we turned to small angle X-ray scattering to understand how this tetrahedron forms. And we saw something quite surprising. So again, we can simulate the scattering data of the tetrahedron, and then we can monitor the reaction solution of this 10 peroxides per 1 zirconium solution and see what forms on the way to obtaining this tetrahedron that crystallizes out a solution. What we found is something much larger forms. And we know it's larger because we've got a shift in the Guigney region to low Q region. And it's something quite pure. And we know that because we see this oscillation here. Okay, so we've never been able to crystallize that, but based on the size, it's about 22 zirconium polyhedra linked into some sort of cluster form. All right, so this summarizes a lot more information than I have time to talk about, but just following this path here. So we start with our ubiquitous aqueous form of zirconium, the flat square. We add a ton of peroxide. Zirconium actually catalyzes decomposition of peroxide and forms oxos. And the oxos link the zirconium into this fluorite-like structure, similar to the UO2 story that you may recall, but in a molecular cluster form. And with time, it breaks up into these tetrahedral clusters that we crystallize out. Okay, so in order to save some time for the niobium story, I'm going to summarize here and say that hafnium and zirconium in solution, even though in the solid state they're absolutely identical, infamously identical, difficult to separate, in solution they have intriguingly different chemistry. We've learned a little bit more about peroxide, which is important in photochemical lithography. And in this fundamental study that I just presented, it also promotes assembly, disassembly reactions of multinuclear clusters. Okay, so third story. So now we're going to up the periodic table from uranium just to the right of zirconium and hafnium, and we're looking at classic polyoxometalate chemistry. Okay, so for those of you not familiar with polyoxometalates, this is the ubiquitous aqueous chemistry of group 5, group 6 metals with no electrons, so in their highest oxidation states. So like uranium, they form this multiply bonded oxo that is inert to linking or bridging or reactivity, but only one, not two. So on the other side of this distorted octahedral unit, you do your hydrolysis and condensation reactions, and you form spherical clusters like these so-called Kagan ions. So that's 12 octahedra around the central tetrahedron, and the Lindquist ions. So this is 6 edge-sharing octahedras. So those are two very typical polyoxometalate structures. Okay, so the cluster that I'm talking about today is decaniobate, and that is shown here. So you can think of it as a 6-pack, so 6 octahedra in a 6-pack arrangement with 2 above and 2 below. And I call it the brick and mortar building block for cluster-based materials because depending on the solution you put into it, it can act like mortar. Okay, so if you throw it in water with basically anything, the structure form changes and then links together into larger species. If you throw it in methanol, this cluster acts like a brick and builds up materials in this intact form. Okay, so let's take a look at the mortar behavior first. So this is Raman spectroscopy, and we have dissolved this decaniobate cluster with its 6 tetramethyl ammonium counterions, and added just alkali salts. And we can monitor changes in this cluster over time. And what we see is this peak here, let's just call it the fingerprint peak for this goes down and then another peak grows in. And moreover, there seems to be a periodicity to this where you get a faster reaction with the larger alkalis. So after 3 days with cesium, rubidium, potassium, your decaniobate is completely gone. But your sodium or your lithium and your sodium solution is still converting. Okay, so this is indeed dependent on the alkalis. Here we are monitoring the disappearance of that decaniobate fingerprint peak with lithium, potassium, cesium, 3 different concentrations. And with 6 equivalents of cesium, the reaction happens extremely rapidly. With 3 equivalents, oh, I don't even see it on the graph, but with 1 equivalent, it's much slower. And then the slowest, 1 equivalent of lithium, it's extremely slow. After 90 days, it still hasn't converted completely. Okay, so clearly the alkali is doing some chemistry here. And this is unusual because polyoxometalate chemistry is usually controlled by pH. Okay, so we monitored the pH, and mind you, we're not adding acid or base. This is just the pH that is controlled by protonation or deprotonation of this cluster as it undergoes whatever chemistry it's doing. And so the black is our standard. So just just tetramethylammonium decaniobate is completely neutral. Now, when you throw in alkalis, the pH raises to about 8.5 or 9, so it goes up to mildly alkaline conditions, and it just stays there. We can buffer the reaction with heaps and add our alkalis, and we can keep the pH down to around 7, 7.5. But does the reaction still happen? And the answer is yes. So again, we're monitoring the disappearance of that decaniobate peak. And so this is the buffered solution. This is the unbuffered solution with cesium. And we can see that that decaniobate peak goes away, but not as fast. Okay, so we turn to SACS to see what else we can learn about what's going on in the solution. So sorry, this is kind of small, but again, the black is our decaniobate. And then with our increasing alkali size, we get increasing scattering. We get a shift in the GDA region to low Q region. And this again is very beautiful scattering data that shows a very nice trend that we are forming monodispersed solutions of some large cluster, and they get bigger with larger alkalis. Okay, so we could not crystallize these out. And that's why I'm going into this extensive solution characterization. Because this, again, we wanted to publish it in JACS, so we needed to understand what's going on. So we turned to the literature, and we had a hypothesis, and that is that when you throw the alkalis into solution with the decaniobate, it's shearing off 3 of those octahedra, so we get this NB7 intermediate with these oxos terminal, 3 of them that are very reactive, so it links together in this NB24 ring. So this was crystallized in 2006 with copper amine counter ions. Okay, so, but here we've got simple solutions. We don't have anything fancy like copper amines. Okay, so we had a hypothesis that what's forming is this NB24 ring. And so we simulated some scattering data of linking these NB24 rings together with different alkalis. And here we've got 2 of these NB24 rings linked together with lithium. That's the simulated scattering data. It fits very nicely with the experimental scattering data in red. So we're pretty confident this is what's happening. We also proved it by mass spec. With larger alkalis, we still have the NB24 unit, but they're just linking into larger aggregates. So 3 or 4 of these linked together. And that's just what larger alkalis do. They undergo direct bonding in water. Okay, so this is work that was done by a PhD student who defended in 2018, and Alex Navratsky, some of you may know her, was on his committee, and she said, if you have a reaction where you are not adding acid or base, you need to be able to write a balanced chemical reaction. So it turned out this wasn't easy. The only way to do this is to include a polycationic fragment, which is not expected in polyoxometalate chemistry. So polyoxometalates are negatively charged. With this hypothesis in mind, we checked by electrospray mass spec, and indeed we found this niobium-3 cationic fragment that is sheared off that decaniobate, and this is the other part of the solution. The small part that we are not seeing by X-ray scattering and so on. Okay, so we successfully published this in JACS, and the theme of this study is we are promoting chemistry with alkalis only, not with pH. Okay, so this is a very unusual mechanism to drive chemistry in water and with polyoxometalate chemistry more specifically. Okay, but again, we like structures and we still weren't satisfied. So we were never able to crystallize anything out of these solutions. They would just turn into gels. And this is ideal for thin film deposition. We're doing that too. But meanwhile, we want to absolutely prove that we have this NB24 unit in solution. So looking at the structure, we said,